And we're back. Welcome back and happy Thursday. Today we will continue on with our discussion of the image domain, and the focus of today's module will be on representations. How do we depict or how do we describe the content of an image? And so last time when we talked, we discussed this notion of looking at differences of imagery or in imagery, and we talked about there are many ways you can depict or describe these differences. For example, the size of the fish are different. The particular shade of blue is different from one fish to the next. The color might be different entirely, or the direction in which they're pointing. We also talked about this notion of how you represent things that move in a picture, and you can take that image from one time instant to the next, and you can treat that either as a single camera that moves or two cameras at different positions, and using triangulation, you can recover the depth, the distance of that object depicted from the camera. We also talked about the correspondence problem. In that correspondence, you tried to find where in the new image, a particular patch or region of the original image did that object described go. And so we have a number of candidates in the new image at time t1, and you literally search for the image content in time t0. And we need some measurement of similarity in order to do this, and things like correlation that we discussed last semester in stochastic computing is one of them, but not the only thing. So let's take a look at so-called intensity surface representation, which is how you describe the content of an image. So we're given a grayscale image, and it's not too much different to do this in color, but we're going to focus on grayscale, and then a few slides maybe in the next module, we'll talk about how you depict color information. So you take your grayscale image, and you lay it down like a carpet, and we impose a set of axes that allow us to describe the location of a pixel in this grayscale image in so-called image coordinates. And so here we have pixel at x1, y1 in image coordinates, and this particular gray pixel is going to take on a value, and it takes on a value that's between 0 and 255 on the integer number line. So 0 represents black, and 255 represents white, and all values in between are shades of gray. And so a gray level that is closer to 0 is a darker gray, and a gray level that's closer to 255 is a lighter gray. And so we call the function that gives you for a particular coordinate in image coordinates that gives you a gray level, we call that our intensity function. And so now you can imagine the image is a two-dimensional function that takes on gray values, that's the range, 0 to 255, at every location in image coordinates x, y. And so let's think of gray values, these intensities returned by the intensity function for the image. Let's think of these gray values as the height or the size of the intensity. And so for image coordinates x1, y1, it has an intensity value. And let's imagine that we're 100. And to jar your memory again, for a gray level image, each of these intensity values represents an equal mixture of red, green, and blue. So you can map literally between color and grayscale, which is some mark along the main diagonal in RGB color space. So let me set the pen here, and we'll do some annotation. So at location, or pixel at location x1, y1 in image coordinates, we have an intensity surface level of 100. So let's take this intensity level of 100, and if we were to project that onto the so-called intensity axis, that's this z-axis here, the height of which represents the amount of intensity we find at image coordinates x1, y1. So I'm going to depict that by drawing this spike here, and the height of this spike is going to be the intensity level of this intensity function at image coordinates x1, y1. And so if we have that for one pixel at x1, y1, we can certainly have it for another pixel at another location at x2, y2. So let's imagine, for the sake of example, the intensity level at x2, y2 in image coordinates is 160. And this particular pixel is going to be more white. It's a lighter pixel, whereas the pixel x1, y1, which had a value of 100, is going to be a lighter, darker gray. It's a smaller value. So then let's imagine x3, y3. It has an intensity level, gray level of 160. And then lastly, x4, y4, imagine that had intensity level, grayscale level of 100. So now we have our points. And the thing that we want to do now is take these points and use them to characterize the shape of the intensity surface. And so these intensities form a surface, and collectively all these pixels, if you were to plot the intensity in this representation, it's going to have some surface that has certain terrain features, if you will, a type of relief map. And when you want to characterize the content of the image, you're trying to evaluate where the flat planes are in this intensity surface, where do you find it's bumpy, or where do you find the hills, the inclines and the declines. And so let's imagine our intensity surface if we go from coordinate x3, y3 to x4, y4 in image coordinates. Now, of course, when we go from x3, y3 to x4, y4, we're going to have a change in the pixel, and we're also going to have a change in the intensity value. And so if we were to measure the slope, rise over run, for the span of pixels across which we walk when we go from x3, y3 to x4, y4, as well as the change in intensity, slope is rise over run. So the change in rise, well, in this case, it's negative because it goes down in intensity. And the run is going to be the difference, how many pixels we walk from x3, y3 to x4, y4 in image coordinates. And so if we want to characterize the features describing the content of the image, we're going to use statistics over the intensity surface to tell us about the content of that image. And it's these statistics that we use to make comparisons so we can say, does this image or do these images contain the same content, or how similar is the content between images? Now, how are we going to do this? Well, we use the tools of differentiation, the derivative, and compute a so-called spatial derivative. And this is nothing more than a partial derivative in each direction along a so-called scan line. Now, of course, our principal axes for image coordinates, we have a notional x-coordinate going from left to right, and then we have a notional y-coordinate, if you will, going up and down. And so if we trace along a scan line going across the image, if we compute the slope locally from pixel to pixel to pixel, that slope of that intensity surface, that's going to tell us something about the content of the image along that particular scan line in the x direction. And so we can also do the same thing in the y direction. We can compute the local slope as we go in the y direction for one slice of the image, another slice of the image, another scan line, and so forth. And so when you think about the content, let's take a look at this vertical edge that represents right there the edge of this feature or structure on this architectural wall. And so as we scan across in the x direction, we go from dark pixel, dark pixel, dark pixel, dark pixel, and all of a sudden we go to light pixel. And so a vertical edge is nothing more than a local slope in the intensity surface where the scan line along the x direction had a very large slope, a very large value for the derivative of this intensity function in the x direction. And so an edge is nothing more than a large slope in some direction, for example, the x direction. And if we can do it in the x direction, certainly we can do it in the y direction. And so a horizontal edge in the image represents a change along a scan line in the y direction, going from dark, 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 all of a sudden light when we get to this point. And so if we were to trace the derivative in the y direction, a horizontal edge in the image, that content, is represented as a peak or a large slope for the derivative along the scan line in the y direction in image coordinates. And so one of the things that we enterprise to do, you notice that the edges tend to be very prominent. And so if you can isolate the notional largest edges, you can find the important edge features, as it will, describing things in the image. And so this idea of extracting large images, we can use things that we've learned at this juncture, things like percentiles and things like outliers, to say, okay, among all the derivatives representing edginess in the intensity surface, what are the top 5% strongest edges, those that have the top 5% largest slopes? And so this is like hypothesis testing, and it exactly is a form of hypothesis testing, where we're using directly this idea of what it means to be atypical in a distribution to try to extract things that are useful descriptors of an image. And so we have our edges, and a vertical edge is nothing more than a large value for the partial derivative along the x direction scan law for the intensity surface. So let's take a look at the definition of the derivative, and let's abstract this idea of peaks in the partial derivative along the scan lines in image coordinates as a way you represent it. And let's reduce it to something that is computational account of this partial derivative. And so here, let's go back to first principles in calculus that you learned way back ago, and let's go to the definition of what a derivative is. And you learn something like the derivative d dx of some function of x, f of x, is nothing more than the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And so you learn something like this. You have your function, f of x. Let's say this is our f of x. Here is x along the horizontal axis, and here's f of x along the vertical axis. And so what did you do here? You said, okay, well, this value, let's say I have my x value here. So there's my x, and the value here is that value of f at our x. So that's our f of x. And then we go some distance, delta x is delta x, some change, and it can be to the right or to the left, it doesn't matter, but the convention I'm going to choose for this description is going to be going to the right. It's going to increase. So let's say we have some delta x. Now this value, that's going to be x plus delta x, okay? And so if we look at the value that f returns for that point, delta x away from x, that's going to be f of x plus delta x. And so what this is setting up, this definition of the derivative, it says this rate of change of f of x dx is nothing more than the slope. It's the rise over the run. So what is the rise? Well, the rise is this distance. That's nothing more than f of x plus delta x minus f of x. And the run is this distance. That's nothing more than delta x. And so when we take this limit as x goes to 0, what that's saying is we compute rise over run. But when we compute that rise over run, x, we make that delta x as small as possible. So that's what it means to say in the limit as delta x goes to 0. We want this delta x to be so small that we have a little tiny sliver, and this f of x plus delta x, we can think of this sliver as being that local slope. And so here, what this delta x says is make that sliver as small as possible. And if we do that rise over run for as small enough as possible sliver, that is just the local slope at that function for that particular point. And so what this says is let's make a discrete approximation for the rate of change by making that run part as small as possible. Okay, so if we make that run as small as possible in the image, well, how might we do that with an arbitrary function? Well, with an arbitrary function, if you want the slope at a particular point, you're going to take that x value and you're going to go to the left and to the right of it. So when we do that, we're taking a line and we're taking the slope, the rise over run, for the closest way you can go less than that x value and the closest way you can get above the x value. and you're taking that line, imagining it's the hypotenuse of a right triangle, and now the delta x is just the length of the base, and the f of x plus delta x minus f of x is just the height. Now, that's our function f of x, but here for the image, the raw content of the image is just the set of values returned by the intensity function. And so if we're going along the scan line in the x direction in image coordinates, well, we're taking the partial derivative dx, partial derivative with respect to x, because we're along the x scan line for this example, of that intensity function. Now, of course, this intensity function is a function of x and y, but because we're taking the partial derivative, every part of that intensity function, which is a function of y, is going to be considered a constant, and when you take this derivative, that constant goes to 0. So how do we do this in practice? Well, if we want the slope at some point x, we need to go to the left of x, that's x minus 1 for that x coordinate, and to the right of x, that's x plus 1, in order to compute the run part of this rise over run for the computation of slope. And so if that's the case, we're at some location x in image coordinates, the best way we can make delta x small, delta x goes to 0, is to go 1 pixel to the left and 1 pixel to the right. And so therefore, if we look at this expression, our f of x plus delta x, well, here we're going to the right of our x, so that's 1 pixel. So this is to the right of x. And this term represents to the left of position coordinate x in image coordinates. And so the y doesn't change because we're on a scan line in x. And so if we're going to compute the local slope at point x along the scan line in the intensity surface, we would take that difference, this is the rise, the numerator, that's the rise, I of x plus 1 comma y, minus I of x minus 1 comma y, that's the rise, and then the run, the denominator, is just 2, because you're going 2 hops in pixels from x minus 1 to x, and then from x to x plus 1. And this is going to be the expression, the discrete approximation to the partial derivative of our intensity surface in image coordinates. So now we take this expression. If we look at this expression for the partial derivative d dx for ixy, we can rewrite this expression by decomposing all the terms. And so here we take the first term and we can write that as plus I of x plus 1 comma y over 2. And the next term we can say minus I of x minus 1 comma y over 2 plus 0 in the middle does not change the expression. And so if we organize those terms, we can re-express our partial derivative along the x scan line as minus 1/2 I of x minus 1 comma y plus 0 times I of xy, because 0 times anything is 0, plus 1/2 I x plus 1 comma y. Now, if we do this, we can cast this computationally. These weights, we see a weight of minus 1/2, a weight of 0, a weight of positive 1/2. And so I draw your attention to this mask, and this has a name. It's a so-called convolution mask. And this mask is going to be populated with the coefficients in this expression for the partial derivative of ixy with respect to the x scan line in image coordinates. And so here we see the minus 1/2, that leading coefficient, 0, and the 1/2. Now, of course, the values of the pixels in our intensity surface, that's our I of xy. And so if we take this mask and we center it in image coordinates at coordinate x comma y, well, the coordinate to its left is x minus 1 comma y, and the pixel to its right is x plus 1 comma y. And so if we take the product of each one of these values in our convolution mask with the pixel that it sits over. If we were to place this 3-pixel wide mask over the image, this result, this weighted sum, 1/2 times I of x minus 1 comma y, plus the 0 times whatever the intensity surface is at that coordinate, plus 1/2 times whatever the intensity surface is at that coordinate, the resulting sum of those terms is exactly the value of this partial derivative. Now, this also has another term in the literature. It's called the central difference. It's taking the difference, rise over run, at the particular point in the intensity surface over which that convolution mask is centered. And that's the slope of the intensity surface. If this is my point x, and that's my intensity surface, it's that slope that we talked about before, which is using that tangent line and measuring the rise over, here's rise, over the run. And so if we compute this convolution using central difference, the value we get as a result of that weighted sum is going to be the local slope of the intensity surface at that center position over the image where it is currently placed. And so if we do this in its current position, and then we slide this mask 1 pixel to the right, recompute it, and slide it to the right, we can replace all the pixel values for the center position of this mask with the resulting central difference, this partial derivative. Now, once we slide it to the right and we get to the end of the image, we go down 1 pixel and slide it again, across, down 1 pixel and slide it again, across. And so this successive calculation of the central difference, replacing the pixel value, and then moving it in some schedule of sliding and going down is called a convolution. And so this convolution mask represents the coefficients, in this case associated with the derivative, the slope, in the x direction in image coordinates, and it will thus depict, and you can use it to detect the vertical edges. Okay. Now, of course, if you have a central difference along x, you also have a central difference along y. Now, this results in a slope centered at each image coordinate, and the slope involves a statistic. This statistic uses a sum. It's this term added with that term, and we multiply by 1 over 2. In this sampling, the samples that we take are every 3 pixels. Here's sample number 1, ix minus 1 comma y. Here's sample number 2, ixy. Here's sample number 3, ix plus 1 comma y. And so with this, you can isolate the steepest edges and therefore find the edges, whether they're horizontal or vertical, in the entire image. Okay, and so let's take a look at this in Matlab. I will meet you in Matlab. So we're here in Matlab, and we'll start out by reading in an image. In second line, we have the name of the image, and we're going to read it in. Fourth line, I am read. We're going to measure its size because we're going to need to know how many pixels we have, rows and columns, to help us figure out image coordinates. We're going to convert this color image to grayscale in line 8, and we're going to name the original one image I that we get in, and the grayscale version, we're going to call that IG. So here, we're going to show the original image, and we're going to show the grayscale image. Then here's our central difference operator, our convolution mask. We have those 3 array, or 3 vector, populated with those coefficients for the discrete approximation of the derivative that will give us the edge features. And so we go through some iterations in x and y, and we compute the left value, that term, by convolving that mask, the center value, which has a 0, and the right value. And so we do that inside of our iteration, going along the x scan line for a fixed y, then we change y, and then the next scan line. So we take our discrete derivative at that point, which are the 3 terms, the left-hand term, the center term, which is 0, and the right-hand term. And then we wrap that as an unsigned 8-bit integer so that we can represent that as our new grayscale image depicting the edge intensities, the so-called edge map. So then we display the edge map here in lines 58 through 61, and then we compute the 95th percentile value, that value that exceeds 95% of all of the local slopes in the intensity surface. Given that value, we go through our edge map and we extract out those that are greater than the 95th percentile, so the strongest 5% edges. So then we reconstruct that and we display it as an image, our so-called filtered edge map. So let's go ahead and run this. We run it. Well, we'll organize this based on the same ordering that we discussed them. So in the upper left-hand image, we have the original image of the 46th presidential administration for the United States President. We have President Joe Biden and Vice President Kamala Harris. Now, in the upper right-hand corner, that image, figure 2, that's the grayscale image. So that's the reweighting of the color values for the red plane, the green plane, and the blue plane equally to represent the equivalent value for each pixel along that main diagonal in the RGB color cube, or color space representation. Now, if we come down to the lower left-hand corner, that's the complete edge map. These are all of the slope values representing the local slope for each pixel in the grayscale intensity surface. Now, you notice the grayscale image is brighter than the edge intensity map. In the intensity map, you can see literally all of the pixels, but it's a slope depiction and not a color depiction. So let's look at this last image on the lower right-hand corner. That's the filtered edge map. That's the top 5% strongest edges, but these edges are the edges that you get if you use the scan line in the X direction in image coordinates. And if you look at it, well, here you have the right shoulder of President Biden. You notice that strong edge. We have this edge here going from dark for his suit color to light, the shirt color. And then you see where their arms and shoulders touch, there's no edge. And you notice that this edge between Vice President Harris's jacket and President Biden's jacket, that's not a very strong transition. It goes from dark black to moderately less dark black. Likewise, if we look at the jacket collar for Vice President Harris, that's not a very big difference, but when you get to her necklace, that is a big difference, or the difference between her neck and her shirt in intensity and grayscale, it is a big difference. But certainly you see Vice President Harris's left shoulder, because that's a big change in intensity surface going from her jacket color to the color of the wall behind her. And so this represents the partial derivative in the X direction for all of the X scan lines, representing all of the vertical oriented edges in this image. All right, so you can certainly do this in the Y direction, but my purpose was to demonstrate this for X to go with our conversation in PowerPoint slides. So let's go back to PowerPoint. I will meet you in PowerPoint. So that's a real demonstration of what you can do to extract the content and describe the content in the images. We ran a statistic, an operator, the convolution operator, to give us the local slope of each one of the pixels in the intensity surface. And now you can take things like distributions over these edge maps, these gradients, these derivatives, to tell you things about high-level content in the particular image. All right. So with that, we'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.